So this week we are covering acids and bases and the chemistry of acids and bases and how do you recognize them? What are the characteristics there of these substances? So the water and acids and bases. So water gets confusing when you're trying to define acids and bases because water acts like an acid and a base. So water could be both and it has to do with hydrogen atoms. So scientists back in the 1800s had this really difficult task of how do we define acids and bases? And it came down to mostly hydrogen atoms. So the hydrogen atom in a water molecule has one proton and one electron, and it shares that with oxygen. So in water, you have H2O, and so that hydrogen and oxygen are bonded together, and they're sharing an electron. And the proton can transfer to another water molecule because of the stronger pull of oxygen compared to the pull of hydrogen. So water could just toss off one of its hydrogens and give it to another water molecule. And so here you have water and water. And this hydrogen can go over there to this water molecule, and this will form a substance called H3O plus, which is called hydronium, or it'll form OH minus, which is hydroxide. So somebody is giving up a protein and somebody, or proton, someone is giving up a proton and somebody is getting one. So this guy got one and this guy gave one up. They can also go back, so you can give back that proton and go back to being two water molecules. So this transfer of a proton creates two new molecules. Like I said, H3O plus, this is called hydronium, and OH is called hydroxide. And a proton transfer from the H3O plus ion back to the OH ion makes water again. So I have an animation here of that. All right, so here are two water molecules. I hit play. You can see in here, this is the hydrogen, and it's got one electron, and it's got one proton. And you just transfer over the proton, just the proton. The electron stays over here, just the proton. And that makes this H3O plus, and that makes this OH minus. So remember, this is hydronium and this is hydroxide. And this can happen in water back and forth, over and over and over again. They give it back. Just this keeps going this way in water. So what does that have to do with acids and bases? Well, in pure water, the number of hydronium ions is in balance with the number of hydroxide ions. So even though you're making acid and base, so hydronium is acid and hydroxide is base, overall the pH is 7 because you have equal amounts of acid as you have base. But if you add an acid to the water, this will upset that balance of hydroniums and hydroxides, and it will add more protons to the water. So it's going to toss in more hydrogens to the water. And this is going to increase your concentration of H3O plus because you're adding in more H's, and so more water molecules are going to suck up H's and become H3O pluses. So acids donate protons, and indicator molecules will then change color. You'll see indicator molecules, but they're anything that changes color in an acid or a base. There's a couple of them like universal indicator and litmus, and if you're coming to in-person instruction, you'll find one in cabbages this week. So I have an animation of that too. All right, so you put in an indicator molecule, and whatever this indicator molecule is, when you first put it in, it doesn't do anything. So you add acid, those acids add these little protons that then increases the concentration of H3O plus. Now there's two more H3O pluses. Those H3O pluses then donate protons to indicator molecules, and then the indicator molecule gives some sort of resulting color change that tells you, hey, this is an acid. So you're going to see indicator molecules this week, whether you come to in-person or you do virtual labs. But, through looking at these indicator molecules, that's how we can tell if we're working with an acid or a base. So they're really handy. So acids donate protons, bases take them. So a base added to water takes protons from the water. This increases the concentration of OH minus because you stole an H from the water, and the H3O plus ions and the indicator donate protons to the OH ions, and this decreases the concentration of H3O plus, which then results in the color change. So I have a animation of that one too. So this is water. You've got an H3O plus ion hanging out over here, and then one OH over here, and that's in balance, 1 and 1, and everything else is just regular water. We add a base. Bases suck protons out of the water. Then they suck protons out of indicators as well, and that causes them to turn a different color. When indicator molecules lose protons, they change to a different color, and that says, hey, you're working with a base. All right, so what are other characteristics of an acid? So chemical substances, typically corrosive, meaning they can dissolve things. Acids in particular are very corrosive to metals. They're also corrosive to some kinds of rocks like limestone. They can also be corrosive to your skin. So if you need to get rid of a body, you can dissolve it in acid. Because it does dissolve a lot of things. It's not going to dissolve your bones though. They are sour tasting, so if you lick an acid, it tends to have a sour tasting. The word acid is actually Latin for sour. You're going to neutralize alkalis, so if you add an acid to a base, you get a neutralization reaction, and then it dissolves metals, like I said, and it turns litmus red. So litmus is a kind of chemical. It comes from a plant. And litmus turns red for an acid, and it turns blue for a base. So if you're coming in person, you'll work with some litmus this week, um, and that's just one of the characteristics of acids. So like I said, lots of things that you already know are acids, and a lot of times people say, acid, oh no, that's really dangerous, but it's not. So a lot of things you already interact with on a daily basis are acids, like juice is an acid, tea is an acid because it has a tannic acid in it, and then soda is an acid because of carbonic acid. The way an acid affects you is not just like all acids are bad. Some acids are more corrosive than others, but in general, no acid is bad or like dangerous. You interact with acids all the time. It's their concentration that can make them dangerous. And then, like we said, they taste sour. These sour warhead candies, if you've ever eaten them, you'll notice a white powder outside of them. That white powder is 3 different kinds of acid. So that's what makes these taste so sour, is that acid powder. So it's an indicator. Like we said, there are compounds that can change color in the presence of an acid or a base. You're going to see them this week either in person or through a virtual lab, but they're really handy because you add an indicator and then it tells you, hey, this is the level of that acid or base. So acids turn litmus paper blue. Okay? So if you take red litmus paper and you add blue to that, then that is an acid, and that comes from a plant called the lichen plant. So blue litmus paper turns red for an acid. Acids make hydronium, like we said, when they are added to water because they donate protons to the water, thus increasing the concentration of hydronium. And then there's this thing called the pH scale. So pH is a measure of the concentration of hydrogen ions. So how many hydrogen ions are there? So it's percent hydrogen, and that's what pH is. And substances with a pH less than 7 are acids. So 6, 5, 4, 3, 2, 1 are your acids. And so they could be, hydrochloric acid. They could be, this is like the acid in your stomach. They could be like lemon juice. Lemon juice is a pretty strong acid, but you wouldn't be worried about swallowing some lemon juice. It's not going to kill you. Apples are acidic. Vinegar is acidic. Tomatoes are acidic. Bananas are acidic. Even milk is slightly acidic. So lots of things that you interact with on a daily basis are acids. So it's not like all acids are going to kill you. And then in the middle, there are neutrals. So if you have a pH of 7, you're not an acid or a base. You're a neutral. And differences on the pH scale. So the pH scale is a base of 10. So the difference between one number on the scale and another number is 10 times the concentration. So a pH of 9 is 10 times more basic than a pH of 8. Even though they're only one number apart, it's a 10 times different, which is why when you have, an acid, if you go back to the scale here, You can have, stomach acid, which will literally dissolve your skin. And just right over here is lemon juice, which is not that big of a deal. But that's because this is 100 times more acidic than the lemon juice. Even though it's only 2 numbers over, it's a scale of 10 each time. So small differences on the pH scale can make big differences in the danger of these chemicals. So what's a base? A base is any water-soluble compound that is capable of turning litmus blue, reacts with an acid to form salt and water. So many familiar substances are bases, like soap is a base, drain cleaner is a base, baking soda is a base, and one property of bases is they often taste pretty bitter. So things like, imagine if you put soap in your mouth, that's what a base tastes like. They have a bitter taste rather than sour like acids. When bases come in contact with your skin, they feel slippery. So like that feeling that you get from soap or cleaner, that comes from a base. Bases tend to have that slippery feel to them. Bases have a pH that is greater than 7, so 8, 9, 10, 11, 12, 13, 14. And we say bases have a higher pH and acids have a lower pH. So if I say, oh, that's something that has a high pH, then I'm talking about a base that may be like pH of 13 or 14, that's a pretty high pH. And then acids, to say a low pH, like the lower the pH, the stronger the acid. So like something with a pH of 1 is a very strong acid, whereas something with a pH of 5 is a pretty weak acid. Bases turn red litmus paper blue. So if you add a little bit, I remember litmus comes from a plant, add a little bit of base to a litmus plant, it will turn blue. Bases make hydroxide, that's that OH, because they take a proton from water. Bases are proton takers. Both acids and bases conduct electricity. So if you dump an acid or a base into water and then try and run a current through it, it will conduct electricity. And they are called electrolytes. That's a term you may hear because everyone's like, Gatorade, you got to replenish your electrolytes. But electrolytes, anything that conducts electricity is something that ionizes in water. And so if you have ions in water, then you can conduct electricity through that. So acids ionize in water. So do things like salts. So salts ionize in water, and that's what you're drinking when you're drinking Gatorade. It's not the acid, it's ions for salt. Acid plus a base equals water and salt. And this is hard for students to understand, but you're like, oh my gosh, if I take a super strong acid and then I have a super strong base and I mix them together, what will happen? Nothing. They'll get water. They destroy each other. You don't get a crazy explosion. So acid plus base is water and salt. That's a neutralization reaction. And so even though these two things on their own are incredibly dangerous, depending on their concentration, the strongest acid plus the strongest base gives you water and some salt. So no acid or base. And this is also handy as a chemistry teacher. So after we're done using a lab with acids and bases, I can mix them together and then neutralize and just get water and salt out of that. And then I can just pour that down the drain. Not all acids and bases have the same concentration. They can be strong or weak. So the way you can tell the difference is if you put a strong acid into water or a strong base into water, it will disassociate completely into its ions. And this is where that electricity conducting comes from. So you'll have these positive and negative charges because they break apart from each other. They disassociate. So here they are bonded, here they are disassociated, and they all disassociated. That makes it a pretty strong acid. But weak acids and bases only partially dissociate. So this is acetic acid, this is vinegar, and vinegar is not a very strong acid. So if you notice here, if you add it to water, most of the vinegar molecules stay connected to each other, but then there's just one that separates. So if you get partial ionization or some dissociation, then that's pretty weak. But if all of the acid or base dissociates into its individual ions, then that is strong. And those are some characteristics of acids and bases.